We're going to do one more problem that involves what we've been covering. So here's another example problem. Y equals x minus 1 cubed plus 2. So let's go ahead let's determine the critical points. Now let me remind you of what the critical points are, and I may or may not have mentioned something that occurs rarely but sometimes occurs. Usually critical points are maxes or mins, and the way we find those is we look for the places where the first derivative is 0. But there's another set of critical points, and it occurs where the first derivative is undefined. Now here's an important point, because later on we're going to have problems where there's no first derivative because there's no function. But this is an example where the values are in the domain, but the derivative is undefined. And let me just give you a couple of examples, and these are very rare. Matter of fact, we will not even do any example problems. So 99% of all the problems we do with critical points are maxes or mins. But let me just point out there are some occasional exceptions. So the first one is you might have some kind of function. Let me draw a graph, and this is pretty unusual, where you're going along here, and then at some point it pretty much goes vertical for a while, so if you think about the slope or the first derivative of this graph, it's positive here, positive, positive, but what happens, what's the slope of a perfectly vertical line? If you recall the slope of like rise over run, if you recall back, if you have a perfectly vertical line, actually the slope is undefined, which means at this part of the graph, the first derivative is undefined. This would be considered a critical point. That's why I wrote up here. Critical points are when the first derivative equals 0 or the first derivative is undefined. A second kind of situation where we can have an undefined derivative, you get these occasional graphs where you have like a point. It's not a smooth curve. As it turns out, because the way we define our derivatives, there is no first derivative at this point. So once again, at this point right here, first derivative is undefined. So this would be considered a critical point. So these are sort of the very rare kinds of occurrences where the first derivative is undefined. And we will not even, I don't think you'll have any homework problems. I won't even do any actual examples of these kinds of problems, because 99% of the critical points we deal with are either maxes or mins. But just beware, critical points can occur both these situations. All right, I want to make sure I covered that because I don't recall in my previous talks whether we covered that. So let's go back to this problem. As a matter of fact, maybe I'll just rewrite it again. Sort of got sidetracked, but that was something I wanted to make sure I mentioned. So now we're going to, I'll list here. We want to find their critical points. And once we find their critical points, we want to know whether they're max or min or neither. And then let's go ahead and determine the intervals where the function is either increasing or decreasing. So once again, the way we learn to answer all these questions are to find their critical points, you first take the derivative. So this is a little bit of a chain rule. Now multiply by the derivative of what's inside the parentheses, which is just 1. Then the derivative of 2 is 0. So this is my first derivative. Now to find their critical points, you take the first derivative and you set it equal to 0 and you solve this equation. This is actually a pretty simple equation to solve. There's only one solution. So there's only one critical point when x equals 1. Now the question is that critical point a maximum or a minimum? So the way we do it, once again, we sort of create our little chart here. Here's 1. In this case, I just have to look on either side of this critical point to see what the first derivative is. Whatever the first derivative is on either side of this critical point will tell me what's happening when x is 1. And once again, I'll say it again. In this region 1, all the way from negative infinity to 1, when x is anywhere between negative infinity and 1, the first derivative of x is always either positive or negative. It does not change. It isn't positive for part of this region and then the first derivative can go negative. No, it's either positive or negative the whole time. And in the same way, when x is between 1 and positive infinity, the sign of the first derivative cannot change. The first derivative is always either going to be a positive or negative number when x is between 1 and infinity. So that's why all I have to do is just choose, like over here, I just have to choose one value of x in region 1 and see what the first derivative is, and then I'll know what the first derivative is for that whole region. And then over here, I need to just choose one point in this second region, go figure out what the second or what the first derivative is when x is 2, and whether it's positive or negative, that's going to be the sign of the first derivative for this whole region. So let's do that. So here's region 1. We've done this before. Basically, I'm looking at what the derivative equals when x is 0. So I'm checking region 1 now. So I plug in x equals 0 into my first derivative, 3, 0 minus 1 squared. So this is negative 1 squared, which is 1 times 3. This is 3. I've just determined the first derivative in region 1 is positive. I could also say that means the slope of the function is positive. A lot of times I'll go ahead and sort of sketch what the graph sort of kind of probably looks like. It's a positive slope. First derivative is positive. Going from left to right, the graph of the function is increasing. Now let's see what happens in region 2. So now I'm going to go calculate the derivative. I'm going to choose, a lot of times they call these test points, 0 and 2 are called test points. For my test point, my point in region 2, I'll choose when x is equal to 2. So I'm going to take my equation for my first derivative. These are both the same. And now I'm going to plug in 2 for x. So this is 1 squared, this is 1. It's 3 again. Once again, a positive number. So I now determine that in region 2, the first derivative is positive, which means my slope is positive, which means my function is increasing. So it's like this. All right. Now this is sort of different because normally the critical points, a max or a min, a lot of times the slope changes. It's a positive on one side and then goes negative, or maybe it's negative and then positive. Here, on the low side of my critical point, it's a positive slope, positive first derivative, and you go to the other side of your critical point and it's still positive. So what's going on there? Well, this is a case where obviously it's not a max or a min. What is it? It's a neither. So what's probably happening is if I go up like this, and then this thing right when x is 1 becomes perfectly horizontal, levels off, but then instead of going down, it goes up again. So you can see when x equals 1, the first derivative here is going to be 0. The same thing happens at a max or min, but instead of now this coming down to form a maximum, it turns around and keeps going up again. And that's why we call this a neither. So we say at x equals 1, that critical point is a neither. So function increasing, decreasing. What are the intervals? Well, you can see from negative infinity to 1, it's increasing. But then also, when it gets to 1, it's not increasing, so I cannot include x is 1. But then as soon as I get past x is 1, it starts increasing again. And I haven't done this, but sometimes when you have two different intervals, what they sometimes like to do is they will sort of union them together, and then you put the second interval. So this says, where's the function increasing? When x is between negative infinity and 1, and also from 1 to infinity. So really the only place on this function, or this graph, where the function is not increasing is right when x is 1, where it levels off. Other than that, it's always going up. As a matter of fact, I went ahead and created the actual graph of this function so you can see it. And you can see here's what it looks like. So you can imagine this is like y, and this is like x, right? So it's going up and up and up, and then you can see how it levels off and it gets pretty flat. And as it turns out, mathematically, we've determined that the place where it gets perfectly flat is when x equals 1. And then what does it do after a little while? Then it starts going up again. So this is my critical point. My first derivative when x is 1 is 0. My slope is 0. But it's interesting how the slope is positive here. So it's positive here, the slope. Goes to 0 at the critical point, and it's positive again. So that's why we call this critical point a neither. It's not a max, it's not a min. It is a critical point. The first derivative is 0, but we call it a neither because the first derivative did not change signs on either side of the critical point. All right, so you will have some problems like that, where you don't have a max, you don't have a min, you have a neither. Maybe some problems you'll have a max and a neither. You don't know. There's all kinds of different combinations. All right, so that wraps up the teaching for this first section, and then what I'm going to do is I'll make a video where I do work through some of the homework problems you're going to be working on.